Okay, this is the exam review for Math 1100. First exam, we're starting with section 1.5, evaluating limits. So question 1, knowing that we have a rational function here and that we need to evaluate this limit directly, that means we plug this value -3 in for all the x's. It's always a good idea to factor if it can factor. So I'm going to rewrite this problem and factor the denominator, because you want to make sure that you're not going to divide by 0. And the denominator factors into product of x plus 2 times x plus 5. So if we directly substituted -3 in for all of these x's here, here, and here, it doesn't look like we'd be dividing by 0, so our expression is still going to be defined. So we just need to evaluate each x as a -3. So here in the numerator, -3 minus 7 is -10. In the denominator, if you plug in a -3 here, -3 minus 2 is -1. If we plug in the -3 here to that x, -3 plus 5 is 2. So we have -10 divided by -2, which is +5. Question 2, going to approach it a similar way. Limit as x approaches -3. I'm going to factor the denominator. So we're going to have x plus 3 and x minus 1. Now if we tried direct substitution right off the bat, we would notice, alright, if we plugged in the -3 right there to that x, we'd have -3 plus 3, which is 0. We can't divide by 0. But we also notice that we have a common factor in the numerator and the denominator, which can factor out. So the problem turns into the limit as x approaches -3 of 1 over x minus 1. And we can now plug in a -3 into that x right there. -3 subtract 1 is -4. So this turns into -1/4. Now for question 3, you notice right here we're taking a one-sided limit, and the plus sign means we're coming x approaches 2 from the right side or from the positive direction. And that's important because the type of graph we have is a piecewise function. There's a discontinuity right here in the graph. So this right here is an x value of 2. This barrier right here, this represents an x value of 2. Now we need to approach 2 from the positive direction. That will be coming from here, from this direction here. So we're approaching an x value of 2 from the positive direction. The limit as x approaches 2 from the positive direction is what y value are we approaching. And as we get closer and closer to an x value of 2, we are getting closer and closer to this point. The y value of that point is -5. So the one-sided limit as x approaches 2 from the positive direction of this function equals -5. That one can just be done graphically. So question number 4 is from section 1.6, where we talked about continuity. Okay. This type of function, a rational function, often has vertical asymptotes. A vertical asymptote would be discontinuity because it separates a graph into a right and a left side. These vertical asymptotes would occur anytime the numerator is equal to 0. So 3x plus 9 would equal 0 when x equals -3. So when x equals -3, if we were to graph this f of x function here, when x equals -3, we'd have a vertical asymptote. So what that means is we don't want this to happen. We don't want x to equal -3. So right now we have a discontinuity at -3, which means it's continuous everywhere else. So we want to find the intervals where the function is continuous. So if it's only discontinuous at x equals -3, then it's continuous everywhere else. So continuous on the open intervals -∞ to -3, and -3 to infinity. And then it says identify the conditions of continuity that are not satisfied. Remember, there were 3 conditions of continuity. The first condition was for a function to be continuous at a value c, f of c has to be defined. So if we're saying it's discontinuous at x equals -3, it's because f of -3 isn't defined. So conditions of continuity not met. First of all, f of -3 is not defined. Okay. The second condition of continuity, which also in this case isn't met, is the limit as x approaches, in this case, -3. The limit as x approaches -3 of f of x also doesn't exist. That's because at -3 there's a vertical asymptote, and if you recall from Math 1050, typically what happens if we were to graph, let's say we have a vertical asymptote here and a horizontal asymptote here, typically what happens is at that vertical asymptote, from the right, the graph will be approaching -∞ down this direction. From the left, the graph will be approaching +∞. So the limit wouldn't exist at that vertical asymptote. So the limit doesn't exist. So those 2 conditions of continuity are not met for this problem. Okay, question 5 is first section of chapter 2. Section 2.1 is we discussed and determined what a derivative is and how it's used. One way it's used is to find the slope of the tangent line at a particular point, but we had to use the definition of the derivative, which involved finding a limit of the slope of a secant line as delta x approaches 0. That's the limit definition, or the definition of the derivative. So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And remember, you can consider y equals in function notation as f of x. Same thing. So f of x plus delta x, if this is f of x right here, 2x plus 3, or 2x squared plus 3, if that's f of x, then f of x plus delta x means that the x right here, we're to zoom in, f of x plus delta x means this x here gets replaced with an open parenthesis, and in that parenthesis I'm just going to put x plus delta x. So that's how I'm going to start. I'm not going to write in the limit part of it right now. I'm just going to focus on simplifying this rational expression. So 2x squared plus 3 is going to be 2 parenthesis squared plus 3. And inside that parenthesis, like I said, I'm going to put x plus delta x. So this expression right here, that's f of x plus delta x. Now I need to subtract f of x. I'm working on this piece now, subtract f of x. All that means is I need to subtract the original function. So subtract, and then the original function was 2x squared plus 3. A lot of students forget to subtract that function using a parenthesis. If you don't use a parenthesis, then you're not subtracting the entire function. And then in the denominator, it's simply delta x. Now we need to continue simplifying. The x plus delta x to the second power is going to become x squared plus 2x delta x plus delta x squared, and then the plus 3, and then here I'm going to subtract. I'm just going to distribute that minus sign into the parenthesis. So we're going to have a subtract 2x squared and subtract 3 all over delta x. Now this expression here I'm going to cross out, and above it I'm going to write an expression where I've distributed the 2. So it's going to become 2x squared plus 4x delta x plus 2 delta x squared plus 3 minus 2x squared minus 3. Plus 3 minus 3 cancel out. Negative 2x squared, positive 2x squared cancel out. So what I'm left with is this expression here in the numerator, 4x delta x plus 2 delta x squared. And then I've got this term here in the denominator, just a delta x. Now, if you notice every term in the numerator, 4x delta x plus 2 delta x squared, each term has a delta x as a common factor. So I'm going to factor out a delta x from these terms in the numerator here. That's going to leave a 4x plus 2 delta x. And then I still have that delta x in the denominator. Now I'm going to write the limit back in. The limit as delta x approaches 0 of this expression here. Now I need to continue simplifying. The reason being is I can't plug in a 0 for delta x yet because I'd be dividing by 0. And that's the reason I factored out this delta x right here, because I can cancel that delta x with the delta x in the denominator. So the problem just turns into the limit as delta x approaches 0 of 4x plus 2 delta x. And now when this delta x here becomes 0, then 2 times 0 is 0. So according to the definition of the derivative of our original function, which was up here, 2x squared plus 3, the derivative we have found here is 4x. Now remember, the derivative is nothing more than a function that's going to tell you the slope of the tangent line at a particular x value. So that's where this next part, find the slope of the tangent line at the point 2, 11. So we need to use this x value and plug it in to that derivative, 4x, right there. Okay. So at x equals 2, slope is 4 times 2, or 8. Okay, question 6. Section 2.2, still talking about rules of differentiation, finding derivatives. But we don't have to use the definition of the derivative anymore. We can start using the rules, like the simple power rule is what we talked about, particularly in section 2.2. Often, though, that requires that we rewrite a problem, especially when the function has a radical. Radicals and derivatives, remember, don't mix too well. So first thing I would do is rewrite f of x using rational exponents. So instead of 3 times the 5th root of x squared, it's going to be 3 times x to a power of 2/5. Now we can use the simple power rule, which remember states this exponent is going to move down in front and multiply the coefficient. So it's going to become 2/5 times 3. So 2/5 times 3 times x, and then the exponent has to decrease by 1, so it's 2/5 minus 1. So simplifying that, 2/5 times 3 is 6/5, and then 2/5 subtract 1 is 2/5 minus 5/5, or negative 3/5. Okay, and technically speaking, if we started in radical form, then we would want our answer to be in radical form. I'd most likely accept this answer, but just to be thorough, let's finish off this answer by putting it in radical form. And also we have a negative exponent. So the negative exponent here, the negative 3/5, means that this term, x to the negative 3/5, this term here is going to hop down to the denominator with that 5. So 6 over 5 times x to a power of 3/5. And then to finish that off in radical notation, it'd be 6 divided by 5 times the 5th root of x cubed. Part B. At this point in the discussions, we hadn't talked about the quotient rule. So we, at that point in section 2.2, wouldn't have known how to take a derivative of a rational expression like 3 divided by x to the 5th. So again, this would have required a rewrite of the function f of x equals 3 times x to the negative fifth power. And like on part A, we can use the simple power rule now. The derivative of f, or f prime of x, this negative 5 exponent is going to move in front of the function to multiply the coefficient. So negative 5 times 3 times x. And then the exponent negative 5 is going to decrease by 1. So we get negative 15x to the negative 6. And with this negative exponent, we can turn it into a positive exponent by moving that term, x to the negative 6, underneath the coefficient, so down to the denominator. That's going to be negative 15 over x to the 6th power. Okay. Question number 7 is just an application of the simple power rule and the sum or difference properties. Even though this is one function, since it's comprised of several polynomial terms, x to the third, 4x squared, and 3, you can take the derivative of each term separately according to the sum or difference rule, or the sum or difference property. So f prime of x, we could start with the derivative of x to the third, which is 3x squared. And then next move to the derivative of negative 4x squared, which is going to be negative 8x. And then the derivative of 3, this is the constant rule, or taking the derivative of a constant is always 0. So you don't need to put a plus 0 at the end because it doesn't affect the value, so we don't need that. So the derivative of f is 3x squared minus 8x. Now we need to find the slope of the line tangent to the function at this point 3 comma negative 6. Particularly, we need the x value because our derivative is in terms of x only, 3x squared minus 8x. So we can only plug in the x value. So f prime of 3 is equal to 3 times 3 squared minus 8 times 3. So this is 3 times 9 minus 24. 27 minus 24 is 3. So it has a slope of 3 at the point 3 comma negative 6. Section 2.3, we talked about some applications of finding a derivative. One of those was the position and the velocity of a falling object. So a ball is thrown upward from a 300-foot building with an initial velocity of 24 feet per second. So first thing we're going to want to do is write the position function. If you remember from the homework, sometimes the position function was given to you, sometimes you had to create the position function. In this case, we need to create it. The position function, the position s at any given time t is equal to negative 16 t squared. Remember, that was the effect of gravity, plus the initial velocity times t, plus the initial height. So our position function is going to be negative 16t squared plus 24, because the initial velocity was 24 feet per second upward, so it's plus 24t, and it was thrown from a 300-foot building, so it's plus 300. So there's the position function. We need to have the position function so we can later talk about velocity functions. The average velocity, remember we talked about this in the discussion in section 2.3. Velocity is just a rate of change That's all velocity is. So when it says find average velocity, you're trying to find the average rate of change. The formula for average rate of change is f of b minus f of a all over b minus a. We have a particular function though, and it's not f of b and f of a, it's s. We're using the function s. So we can replace, if we're looking at this formula here, we can replace the f with s. So s of b minus s of a. And all a and b are two separate x values, or in this case, two separate t values, two separate values of time. And that's what we have right here. We have two separate values of time, a and b, or t1 and t2. So it's going to be s of b minus s of a over b minus a. That's just going to be the position at 2 seconds minus the position at 1 second divided by 2 minus 1. As we pull our calculator up here, the position at 2 seconds, all we got to do is plug in a 2 into our position function. Okay, so a 2 for this t and a 2 for that t. So 2 squared is 4. 4 times 16. It's going to be 64. Negative 64 rather. 24 times 2 is going to be 48. So 48 minus 64. It's negative 16. Then we add that to 300. So the position of this object after 2 seconds is 284 feet. Now we subtract the position at 1 second, s of 1. So now we have to plug in a 1 for all of these t's here and here. No, there's no t there. So t squared is 1 times negative 16 is negative 16. Negative 16 plus 24 is 8, and then 8 plus 300 is 308. That's all divided by 1. So now 284 minus 308 let's try that again. 284 minus 308 equals negative 24. That's going to be in feet per second. Now what this is saying is between 1 second and 2 seconds of this ball falling, or whatever this object is, a ball looks like, between 1 second and 2 seconds, the velocity, the average velocity is negative 24 feet per second. Now obviously between 1 second and 2 seconds the velocity is changing. If we calculated all the velocities between 1 second and 2 seconds and averaged them out, the average velocity will be negative 24 feet per second. The instantaneous velocity is something different. Instantaneous velocity is v of t. It's not an average velocity, it's not an average rate of change. V of t is equal to the derivative of the position function. So in this case, it's going to be negative 32t plus 24. What I'm doing is just taking the derivative of the position function here. So the negative 32t comes from 2 times negative 16 and then decreasing the exponent by 1. And then the 24 comes from the derivative of 24t, which is just 24. Now the instantaneous velocity, specifically at time t equals 2, is going to be negative 32 times 2 plus 24. It's negative 64 plus 24. Add those two together, negative 64 plus 24 is negative 40 feet per second. Now, part C, how long will it take the ball to hit the ground? How long will it take is a question of time. How long will it take means we're trying to find a measurement of time. So we need to solve an equation for t. But which equation? Do we solve the velocity equation for t? Do we solve the position function? How long will it take for the ball to hit the ground? It's not asking anything about how quickly the ball is moving. It's asking how long will it take for the ball's position to be at ground level. For the ball to hit the ground, the position has to be at ground level. Ground level is 0. So how long will it take for the position to equal 0? So when will S of t equal 0? That's the question. So what we have here is a quadratic equation. Negative 16t squared plus 24t plus 300 is what's called the quadratic equation. You studied a lot of these in Math 1050 and Math 1010. There are a couple of ways you can solve a quadratic equation. One of them is by factoring, one of them is by the quadratic formula, completing the square. There's several methods. This one's going to have to be solved by using the quadratic formula. T equals, and usually it's x equals, but in this case it's t because we have a t instead of an x. T equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And the values of a, b, and c come straight from the coefficients here in this quadratic equation. Now one thing I am going to do with this quadratic equation is factor out a common factor between 16, 24, and 300. The common factor, I believe, is 4. Let me just double check. I can divide 300 divided by 4. Okay. So if I factor out a 4, then it becomes negative 4t squared plus 6t plus 75. So now at least the coefficients have gotten a little smaller. This would be a, this would be b, and remember that would be c. So plugging all those into our quadratic formula here, we're going to have the opposite of b, which is negative 6 plus or minus the square root of b squared, or 6 squared, which is 36 minus 4 times a, which is negative 4 times c, which is 75, all over 2a, which is 2 times negative 4, or negative 8, when you're solving a quadratic equation using the quadratic formula, first thing you're going to want to do is simplify that expression underneath the square root. That's called the discriminant. So it's 36 minus 4 times negative 4 times 75. So I'm going to go ahead and work on that. 4 times 4 times 75. That's 16 times 75. Get my calculator out. 16 times 75. That's 1200. You add that to 36, so you get 1236. So this is negative 6 plus or minus the square root of 1236 all over negative 8. Now if you remember from 1050, typically when you solve a quadratic equation you get two solutions. That's why we have this plus or minus here. But in the context of this problem, how long will it take the ball to hit the ground? We don't want two different values of time. We want what's going to end up happening if we were to solve this, we would get a positive answer and a negative answer. It doesn't make sense in the real world or in the context of this problem to have a negative value of time. We just want a positive value of time. So if I think about this, if the denominator is negative 8, I want my numerator to also be negative, because a negative divided by a negative is going to give me a positive value. The square root of 1236, if I were to get my calculator out again, 1236, if we take the square root of that, it's about 35.15. So if I have negative 6 plus 35, that's going to be a positive value. If I divide that by negative 8, I'm going to get a negative value. So I actually just want the negative 6 minus the square root of 1236, because negative 6 minus the square root of 1236. Remember, the square root of 1236 was about 35. So negative 6 minus 35 is about negative 41. Negative 41 divided by 8, negative 8 rather, is going to give me a positive value, because a negative divided by a negative is a positive. So this is going to be approximately, so negative 6 minus 35.15 is 41.15. And if we divide that by negative 8, we get 5.1446. 5.1446. And that's in seconds. 5.1446 seconds. That's how long it takes the ball to hit the ground. Last question here is, what's the velocity at the moment the ball hits the ground? Well, we know it hits the ground after 5.1446 seconds. So the velocity of the ball when it hits the ground needs to be the velocity at that exact moment, 5.1446 seconds. So that's negative 32 times 5.1446 plus 24. Remember, I'm just using the velocity function, negative 32t plus 24, that we had in part B of the problem. So taking this expression, 5.1446, and multiplying it by negative 32, and then adding 24. So at the moment of impact, the ball is traveling negative 140.627 feet per second.
So find the additional profit when sales increase from 10 to 11. So we need to take the profit function and find out what the profit was at 10 units and find out what the profit was at 11 units and find the difference. So the profit at 10 units, if we just plug in a 10 to the function, turns out to be $50. And the profit at 11 units turns out to be $59.50. So the profit increases by $9.50. So what part B is meant to do is illustrate that using marginals you can estimate the rate of change, and it's going to be pretty close to the actual change. So marginal profit is dP over dx. So if you take the derivative of the profit function, so I'm going to rewrite this as -1/2 times x squared plus 20x minus 100. If the 2 drops down, multiplies with 1/2, it's going to cancel out, so it's -x. The derivative of 20x is just 20. The derivative of -100 is 0. So the derivative here is -x plus 20. And at x equals 10, the marginal dP over dx is equal to 10. And since it's a rate of change, it's $10 per unit. So what this is describing is it would increase $10 per unit if we increase production or sales. And that's pretty accurate, because when sales increase from 10 to 11 units, that's an increase of 1 unit. The actual increase in profit was $9.50, and this is saying that it's about $10 per unit. Alright, in 2.3 through 2.5 we learned some more rules and properties of differentiation. This one here, for example, number 10 would be the product rule. So if taking the derivative of the product of two functions, it would be f prime of g, or f prime times g plus f times g prime. So y prime would be the derivative of the f function, which is 6x multiplied by the g function, x squared minus 2x. And then we add the f function multiplied by the derivative of the g function. Okay, and then simplify. Actually, I got this part wrong. Now I'm looking at it. The derivative of the g function is 2x minus 2. Yeah. Sorry about that. So here we'd have to distribute this together, and we would get 6x cubed minus 6x squared plus 14x minus 14. Combine your like terms, and we get 12x cubed minus 18x squared plus 14x minus 14. Question 11 is meant to be an illustration of the quotient rule. So we have an h function here and a g function. So the phrase is low d high minus high d low all over low squared. So it would be low d high minus high d low all over low squared in this case. So f prime of x would be the low function, 3x plus 1, multiplied by the derivative of the high function, so that's -5, minus the high function, h, times the derivative of the low function, all over the low function squared. So that's 3x plus 1 squared. Then we simplify. So this is negative 15x minus 5 minus 6 plus 15x. So the 15x's would cancel, and negative 5 minus 6 is negative 11. And you can multiply this out if you want, or you can just leave it as 3x plus 1 squared. I'm not too concerned about that there on the bottom. Question 12 is meant to be an illustration of the chain rule, because we have an instance of g of h of x, where we have a function inside of a function. H of x would be like the 5x squared plus 2 function, and the g function would be cubing it. So we really have an instance of two functions here. So the derivative of a composition is equal to g prime times h prime, essentially. So we have to take the derivative of the outer function, which would just be dropping down the 3 in front and decreasing the power by 1. So this would be 3 times 5x squared plus 2 to the second power. That's the derivative of the outer function. Now we multiply that by the derivative of the inner function, which is 10x. Okay. I'm going to simplify a little bit here. Finally, we get 750 x to the 5th, 600 x to the 3rd, plus 120 x. Okay, question 13. I'd do a little rewrite here and use rational exponents rather than a radical. So this would be x squared minus 1 raised to a power of 1/3. Now to find the derivative is going to be another chain rule. We have an outer function that's something being raised to the 1/3 power. So let's take care of that. We drop down the power and then decrease the power by 1. And then we take the derivative of the inside function, which is 2x. Okay, now we don't want to have negative exponents. So this term right here, x squared minus 1 to the negative 2/3, is going to drop down to the bottom of the fraction along with the 3. This 2x is going to stay on the numerator, so we have 2x divided by 3 times the cube root of x squared minus 1 squared. Now you can either write it like that with radicals, or if you just want to keep it with a rational exponent, you can write it as x squared minus 1 raised to the 2/3 power. Either would be fine. Okay, question 14 is a product rule. It's x squared times x minus 1 to the 5th power. And then it's also going to include a little bit of a chain rule here. So if we have an h and a g function, remember the product rule is h prime times g plus h times g prime. So taking the derivative of the first part of the function would be 2x times the g function, x minus 1 to the 5th. Now we add x squared times the derivative of the g function, which is going to be 5 times x minus 1 to the 4th power, and the chain rule times the derivative of the inside function. So simplifying here, we get 2x times x minus 1 to the 5th plus 5x squared times x minus 1 to the 4th. Now looking at this term compared to this term, they both have an x in common and an x minus 1 to the 4th power. So factoring out a common factor of x times x minus 1 to the 4th power, if that's factored out of this first term, that's going to leave 2 and then an x minus 1. And then if this is factored out of this, if our common factor is factored out of the second term, that's going to leave a 5x. Okay. And then 2 times the quantity x minus 1, that's just 2x minus 2. Combining like terms inside the parenthesis there, we're going to have x times x minus 1 to the 4th times 7x minus 2. Okay, so for question 15, a higher order derivative, it's just a derivative of a derivative of a derivative in this case. So to find the first derivative, that's going to be 6x plus 7. Okay, the second derivative is the derivative of the first derivative, which is going to be 6. And then the third derivative is the derivative of a constant, which is 0. Okay. Question 16. It's still from section 2.6. It's talking about a higher order derivative because we're going to have to find an acceleration function. The position function. So we have a 30-foot platform. That's the initial height, initial velocity of positive 5 feet per second. So the position function is negative 16t squared plus 5t plus 30. Now how long will it take for the diver to hit the water? This is much like the question on this review from before with the object being thrown off of a cliff. So we need to solve for when s of t is equal to 0. So that's going to be 0 equals negative 16t squared plus 5t plus 30. So if we do the quadratic formula, this doesn't factor, so we're going to have to do the quadratic formula. T is going to equal negative 5 plus or minus the square root of 1,945 all over 2 times a. Now, just like before, it's not going to make sense to have a plus and a minus. This is a value of time, which has to be positive in this situation. And because we're dividing by negative 32, that means our numerator has to be negative. So I'm going to take the negative 5 minus the square root of 1945 over negative 32. This is going to turn out to be a positive value. And this is when the diver hits the water. This is how long it takes. Now, the diver's velocity at impact. The velocity function is the derivative of the position function. So that's going to be negative 32t plus 5. So the velocity at impact is negative 32 multiplied by this value of time right here. Plus 5. So the negative 32 cancels here. So it's going to be, and then the negative and the positive 5 will cancel. So it would be negative 1,945 feet per second. And again, it makes sense that the velocity is negative because the diver is traveling towards the water. Now the diver's acceleration is the derivative of the velocity. That's going to be equal to negative 32 feet per second squared. Okay, so 2.7 implicit differentiation. What we do is we take the derivative of this entire equation with respect to x. So the derivative of y squared is 2y, but since we're taking the derivative with respect to x, we have to do a chain rule with y, because y represents a function of x. So we did an outer function, which is 2y, and we multiply that by dy dx. That's the derivative of y with respect to x. Plus 2x minus 6 dy dx minus 2 is equal to 0. So that's the derivative with respect to x. Now we have to get dy dx isolated. So we need to move all the terms that do not have a dy dx factor to the right side. So it's going to be 2y dy dx minus 6 dy dx equals negative 2x plus 2. And then on the left side, both terms have dy dx, so you can factor out a dy dx. You get 2y minus 6 equals 2 minus 2x. And then divide by the 2y minus 6. So the derivative with respect to x is equal to 2 minus 2x over 2y minus 6. It's a similar situation here. This one is a bit more complicated because we have some product rules here. But in this case, we have a product rule. So the derivative of this first term, 2y squared, is 4y dy dx. Now with this second term here, you can think about this as two different functions. We have an f and a g function, so we have to do the product rule. It's going to be f prime, so that's 8x times g plus the f function times g prime. And then we have the same situation here. So we have an f and a g function. So we have to subtract this expansion. Notice how I'm doing this in parentheses because we're subtracting this product rule. So it's f prime, which is 3 times g plus f times g prime. So it's 2y dy dx, and that's equal to 0 because the derivative of 4 is equal to 0. So distributing the minus sign here, we just get rid of the parentheses and change that to a negative. And then it's a similar situation as the problem above. We need to get all the dy dx terms on the same side. So this is going to be 4y dy dx plus 4x squared dy dx minus 3x2y dy dx. These are all the terms that have a dy dx factor. On the right side, we're going to have a positive 3y squared minus 8xy. And then if we factor out a dy dx, we're going to have 4y plus 4x squared minus 3x2y equals 3y squared minus 8xy. And then dividing by this term is going to give us dy over dx equals 3y squared minus 8xy over 4y plus 4x squared minus 3x times 2y. Now 3 times 2, that just becomes a 6, so it's 6xy.